Hello and welcome to another day in Math 208. I hope the course is going well for you so far. Today we're going to expand. We've been talking a lot about whole numbers and natural numbers and operations like addition, multiplication, subtraction, division. We're going to expand that to negative numbers, which means we're going to be talking about integers. So remember, our natural numbers are what we first learned to start to count with. Whole numbers add 0 to that. And then the integers, we're going to start including negative numbers. So this lesson is going to talk about operations with negative numbers. It's also going to talk about things like what absolute value means, do a little bit of logic with it, and hopefully including some of the properties emphasized in that when we do a little bit of logic. So it's a little bit of a hodgepodge of a few different things thrown in with operations with integers. Sometimes I get these questions up in my classroom. Students will ask, like, what is absolute value and that sort of thing. Anything that you feel like when you were in high school or middle school or even before that, that you never did quite understand, like what does absolute value mean? Or I get a lot, how come when I multiply like x squared times x cubed, it's x to the fifth? Anything from that, send me an email, ask me that question, because the whole point of this class is to kind of fill in any gaps that you might have had in a previous math course. Not the whole point, but it's one of the things I want to do for my students as well. So let me know, and I'll be happy to answer those questions either with a video or meeting with you and taking care of any type of thing that gives you anxiety in math. I want to clear that out of the way. So let's get started with this week 2 resources. You should be able to find this worksheet right there. It's called Figure Out the Digits Problem. And so you've got this puzzle where each letter Q through Z is representing a different digit, 0 through 9. And you have to figure out what each one is. So this right here, actually, I need to change this to capital because it works with the others, so YZ and XU. So I want you to pause the video, look this over, and you can either look it over on your worksheet. I'm not asking you to turn it in or anything like that. I just want to see if you can figure it out on your own. Don't spend an hour trying to do it, but 5 to 10 minutes try to figure out each letter, and then watch a video when you're ready for some hints. Okay, the first thing, I'm taking you've tried this now, you pause the video. The first thing I'm going to point out here, it says, do you need all the information to solve this puzzle? I'm going to tell you the answer to that is no, you don't. I've taught this enough to where I've seen students work through it, and they work through it in different ways. And each semester I forget the answers to each one. I like to go through and try to look at it again fresh, and I always approach it a different way each time I look at it. But the way I'm going to start this out, if you don't know where to begin, I'm going to look at number 2 here. And I see that t plus w equals t. So what's that tell me about w? And so most students will say, well, w must be 0 if you get t plus w is equal to t. So remember, going back to our properties that we talked about in the previous lesson, we said that we had the additive identity. So we're using the additive identity property here to point out that w must equal 0. So I'm going to write these letters out at the top, and we got w to be 0. So 0 right there. You can write 0 anywhere you want for w if that helps you. Sometimes I do that when I work this out. Unfortunately, I don't see any other w's, but it knocks out 0. Then the next thing I look at is something similar to that. I've got number 6. It says s times v is equal to s. So what's that tell me about v? V must equal 1. So v is equal to 1. Remember, that is our multiplicative identity. So that's what we're using, the property we're using right there, that v is equal to 1. I don't see any other v's on here either. So that already knocks out 2 out of the way. Another thing I like to look at is x squared right here. I know that if I've got the numbers, let's go through 9. Let's write those out. So I've already got 0 to be w and 1 to be v. Now, if I squared 2, I would get 4. Okay, that all works. If I squared 3, I get 9. But if I square 4, I get 16. All right, so it's kind of like that concept of closure. If I'm just talking about the set of numbers 0 through 9, only 2 and 3 give me closure when I square them. 4 and above is going to give me a number that's outside the set I'm talking about. Now, you'd say, well, 0 and 1 also give you closure when you square them, but we've already got those values picked out. So once I know what number is 2 or what number is 3, that will tell me, what the deal with x is there. The next thing, let's see here, that I'm kind of hinting at is r. When I times r by 4, remember, multiplication is a simplification of addition. So I could write this as 4 times r equals z. I know that z belongs to one of these numbers, and so does r. So if I multiply 2 by 4, I get an 8. If I multiply 3 by 4, I get a 12. There's no closure there. Anything larger multiplied by 4 is going to be too big of a number. So think about what that means. That means that, because 0 and 1 have already been eliminated here, r must be equal to 2. And then if r is 2, z must be 8. Oops, I'm starting to write 8 there. Let's write 8 right here, and we've got r to be 2. And so this might be a good point where you can pause it and see if that just knocks over all the other dominoes there. See if you can figure out the rest if you're having trouble to begin with. If you already feel like you got the answers, you can keep watching. So knowing that r is 2, notice we've got number 8 right here. 2 plus 2 gives me a 4. So u is 4. So that kind of knocks that out. So I know u is 4. That's a 4. We've got u's all over the place, don't we? We said r was 2, but we already figured out z, didn't we? We already figured out that was 8. This falls apart pretty quickly once you get a couple of them out. Let's go back to number 7. We said that something squared gave me q. Since 2's already been claimed right here by r, we can now say that x must be 3. And so 3 squared gives me 9, so q must be 9. All right, let's see what else we have here. We got x is 3, so 3 plus 4 must equal 7. So s is 7. Now that we know s is 7, let's see. Well, actually, that didn't quite. I'm just seeing number 4 here. X is 3. And we don't know y, but we do know that q is what? What do we get for q? 9. And so subtracting 3 from both sides on that, we get y is 6. And that only leaves t left, so t equals 5. It's not a bad idea to, well, that one doesn't really help us. If there's another t in here, I don't see another t. So there's no way to really just check it, for a final check. But you can go back through and plug them into all these if you want to check and make sure they're right. The whole point here is, one, to use a little bit of logic. We're going to use, we used a little bit of algebra and some of our properties in there as far as, subtracting from both sides, the additive inverse, the additive identity, those sorts of things we had to apply to solve this puzzle. I think it's a fun puzzle to do. At first it seems a little overwhelming to some people, but it's a great way, I think, to build confidence up into students, if they're at that level where they can attempt it, and you can talk about the properties as you go through it and use a little bit of logic also. All right, so the question, absolute value, what does it mean? I think the main wrong answer I get here is the positive value of something. If you have something like -3, the positive value of -3, yet technically if I told you to take the absolute value of it, the answer is +3. But I don't want you to just think about taking the positive value of it. And certainly don't think about it as flipping the sign. If you describe it as flipping the sign, that's most definitely wrong. Because if I told you to take the absolute value of +3, it's not negative 3. It's still also positive 3. So with absolute value, there are a couple of different definitions. The most technical definition is this. If we want to take the absolute value of x, remember these bars right here are what we symbolize for absolute value, it equals the square root of x squared. So think about what that means. If I have the absolute value of 5, that means the square root of 5 squared. So 5 squared is 25. And then when you square root 25, we're taking the positive root there. It's going to give me 5. Same thing if you have negative 3. Square root of negative 3, quantity squared. Remember, if you're punching this in your calculator, put the parentheses with it, or it will give you a negative 9 as an answer there sometimes. That gives me square root of positive 9. And if we're taking the positive root, we get 3 right there. We take the positive root because it doesn't have a minus in front of it, by the way. Some of you may remember from high school math that 9 also has, if you're looking at the positive and negative root, you could say that equals negative 3 or positive 3. But if I just leave it like this with nothing in front of it, meaning I want the positive root. So absolute value is taking the positive root of that number squared. That's probably the most technical math definition you can get for it. Another one that is popular that I get from students and is certainly fine by me to use is that it is the distance from 0. So if we have our number line and here is positive 3 and here is negative 3, the negative just kind of tell me it's direction. So it's to the left of 0 is where negative 3 is, and positive 3 is to the right of 0. But it's not a distance. The negative part, you don't have like a negative on your ruler. If you're talking football, if you talk about somebody that gets, like a quarterback that gets sacked 5 yards, on his stat sheet, it shows up as a negative 5. But the actual distance he traveled, if you went out there with a yardstick to measure it, would be negative 5. I'm sorry, not negative 5. It'd be a positive 5 distance. It would just be in the negative direction, the wrong direction. So the negative just signifies direction, but not really distance. And if you've had a physics course, they kind of emphasize that as well, where negative represents direction, but we can't really measure a negative distance. So you could look at absolute value as the distance from 0, where while this is positive 3, the distance from 0 is 3 units, and this distance right here is also 3 units. It's just in a different direction. So absolute value, I would take either the technical definition right here, or I would take this definition down here that a lot of students like to use, where it's the distance from 0. All right, now we're going to get into our integers, talking about addition and subtraction. And if you did pretty well with last week's work, where we went through and did it with whole numbers and natural numbers, then this is just taking it one step further, and hopefully the things you did last week, you can build off of that, and this will make it easy to explain, like when we subtract a negative, why that's adding a positive, and so forth. So the first strategy we're going to look at here is adding and subtracting integers on the number line. And suppose we have these problems right here, these 4 problems, 3 plus 2. It works just like we did when we talked about whole numbers, where we start at 0 and we go out to 3. That gives us our positive 3, and then we're going to add 2 to it. And so our final answer here is 5. So that's all I really need to see something like that, and we did that last time. Going from there, now we're going to add our negative numbers in here. So our first number is negative 3, so I'm going to start from 0, and I'm going to go to the negative 3. And then I'm going to add to that a minus 2. So I'm going to add 2 more negatives to it. And so that puts me at negative 5. So I didn't change direction or anything like that. I was adding a negative number, so I had to continue in that direction, in the negative direction. Negative 3 plus 2. So negative 3, we're going to go to the left negative 3. And then we're going to go to the positive direction 2. And here we end up at negative 1. And then finally we got 3 minus 2. If I go to 3, that's adding 3. Negative tells me to go to the other direction a -2 and end up at 1. There's one more I don't have listed here. Let's subtract a negative. So if I had 5 minus a -4, so the 5 tells me start at 0, go to the +5. So I'm going to the right. This tells me to change direction. So I would be going this way if I was just subtracting a +4. Like if I had 5 minus a +4, I'd be going this way back to 1. But I don't have that. So I'm going to start to change direction, but then it tells me to change direction again. So when I change direction again, I need to go out this way. 1, 2, 3, 4 more that way. And so I end up at +9. So when I say 5 minus -4, that's the same thing as saying 5 plus 4. Now, I think the next model, the chip charge model, gives a better way of seeing like why when we subtract a negative it's plus a positive. But this is one way you could show it, and that's on the number line. So let's look at it using the chip charge model. So we're going to go through the same first 4 problems. Now, we did the chip charge problem before with a problem like this, where we had 3 plus 2. So what I want to see is 3. When you're doing your work here, you got 3 of something, and then you're going to add 2 to it. And then you can say, all right, not as easy as what I can do here on the computer, but you could show it like this with some ellipses around it. Say, hey, I've got 3 plus 2, and I end up with 5 here as my answer. So 3 plus 2 equals 5. And that's pretty straightforward. I don't think I've ever had anybody had an issue with that. The next thing we got here is -3 plus 2. So when we start throwing in negatives, that's when we're going to start using the red chips here, or if you're drawing it, you don't have to color it in, just a circle with a minus in it will work. I've got 3 negatives, and I have 2 positives. So this, we need to introduce a new idea here, and that's when we've got a plus and a minus. That's what we call a zero pair. So I'm going to circle this right here. This is a zero pair. Basically, you can say that those add up to 0. A +1 and a -1 add up to 0. So when I put these right next to each other, you could look at this as canceling out, or they're adding up to 0. So that's one zero pair, that's gone. This is another zero pair, that cancels out to 0, and you're left with -1. So our answer here is -1. Let's look down at this one. -3 plus a -2. So no positives, just negatives here. 1, 2, 3. And then we're going to add -2 to the -3. So adding these up, I'm going to get -5. And so you say, well, over here, what all do I got going on? If I can see your work like this and see how you get -1, that's fine. This makes it a little bit easier to say, hey, you're saying this plus this equals this. Just try to be as detailed as you can when you're trying to show me your work. That way I know you know what you're doing, and you're not just randomly trying things out to see if I'll accept it. And there you go. So our answer is -5. It doesn't hurt to write that in there so I can see it, equals -5. And then we got 3 minus 2. Now remember how our minuses worked. This one we actually did a problem like this with our natural numbers. We've got 3 positives. Now you could look at it as adding -2. So if you rewrote the problem so I could see it like that, that's fine. You could say, hey, I've got 3 plus a -2. It's the same thing. But then you're going to have to bring down 2 negatives and use the zero pair thing, kind of like we did up here, and get a +1. Or you could just show me in your work, if you're subtracting 2 from it, like, hey, see these 2 right here? Take them away, and I'm left with just a +1. And that's fine as well. So either one. If you want to show me, rewrite the problem as 3 plus a -2, you can do that, or you can do it like I've shown you here. This method, though, is going to help you with the next set that we're going to do in here. So we're still with adding and subtracting integers with the chip charge model. I just was running out of room, so I created a second page. And we've got 3 minus a negative 2. So when you're doing chip charge models, this is probably the hardest one that students have to do. And sometimes it confuses them because I don't want you rewriting this problem. Don't rewrite it as 3 plus 2. Technically in math that is correct, but we're learning and I want you to be able to explain why when you subtract a negative it's the same thing as adding a positive. So for this one, be very careful how you do it on the quiz and on the homework because I want to give you full credit for it and I don't want you to, miss out on something that should be pretty easy. So this is a positive 3. So put in 3 positives. Now this says take away 2 negatives. Well, the problem is I don't have 2 negatives to take away. So what I want to do is start adding 0 pairs to the problem until I have enough negatives to take away. So for instance, if I put in 1 blue and 1 red, that's 1 0 pair. So take a look at what we have here. What's that equal to? Well, these would cancel out, and I'm still left with just a positive 3. So I haven't changed the value there yet. But I can take away 1 red one now. Whoops. He's not cloned in together. But that's not enough. I need to take away 2 reds to make this problem work. So add another 0 pair. So just to sum it up, basically what I have here is positive 3 plus 2 zeros. And now I've got some red negatives here, though, I can take away. So remember, this says take positive 3 and subtract away 2 red negatives. So that's what I'm going to do, and I'm going to demonstrate that just by saying, these 2 red ones right here, they're going to get taken away. And what am I left with? I'm left with 5 positives. And so if you didn't quite understand that, rewind the video and watch that again. I think this is probably the coolest thing about chip charge model is how well it shows why we add a positive when we subtract a negative. That's not an easy concept to grasp when you're young and learning math. You might say, minus a negative is plus a positive and go on and just do that. But how many students do you know can actually explain why you're adding a positive instead of just subtracting a negative? Like, what does that mean? Not just be a robot and just do it because that's what somebody told you to do. You can explain why you do it. So if you feel like you got it, go ahead and pause the video and try this one out. Negative 3 minus a negative 2. See if you can get that. So to demonstrate this, we need 3 negatives here. So 1, 2, 3. And this says take away 2 red negatives. So we do have some red negatives here. I don't have to add 0 pairs this time. That's kind of nice. So all I got to do is take away 2 of the red negatives. So there's 2. Take them away. What am I left with? I'm left with negative 1. And so if you think about back in high school, you probably made that plus plus. So it was negative 3 plus 2, which is negative 1. You probably made that plus plus, and it became positive 5. So this equals positive 5. We see it there. But once again, I want you to be able to do it this way right here with adding your 0 pairs. Otherwise, you won't get credit. I've had students before in a quiz come back to me and say, why didn't I get a credit? And this is what they wrote. And they're like, but that's right. Why didn't I get credit? It's because the directions in it said to use the chip charge model. And I want you to see that you know how to do this technique. So I know most of my students can add 3 plus 2. I just want to see, can they show me why it works? That's what I'm concerned about. All right, so try these 2 out and see how you do with those. All right, I went ahead and posted these up. I paused the video, set that up because I know you probably don't want to watch me drag all those over there. But what I've got represented here is 5. That's the first part. And then I need to take away 4 reds. Well, I don't have 4 reds automatically at the beginning of the problem. I got 5 blues. So I added 4 0 pairs. And when I add 4 0 pairs, now I can take away 4 reds. So those all go away. And when they go away, I've got 9 blues left, which means my answer is positive 9. And so if you think about it, if you did it the old way, if you did plus plus, you get 5 plus 4 is 9. On this next one, I've got start off with -1, and I need to take away 3 negatives. So take away 3 negatives. I don't have 3 to take away, I only got 1. So I need to add a couple 0 pairs here. So there's 1 0 pair, and then here is 2 0 pairs. I don't have to add another 0 pair here because now I've got 3 reds that I can take away. So taking those away, goodbye, leaves me with +2. All right, show all of this so that way I know what you did. Don't just write down 2 positives there. Show all your work there. Go ahead and see what I've got here. I've got, 6 subtraction problems. Write out the answers to those and look for a pattern. So pause the video and do that. So 4 minus 3 is 1. 4 minus 2 is 2. 4 minus 1, 3. 4 minus 0 is 4. 4 minus a negative becomes, well, let's say you didn't know what subtracting a negative was. You didn't know it was adding a positive. Here's a case where you can start looking at the patterns and saying, as these numbers get smaller that we're subtracting from 4, the answer is getting larger. And so this 2 should continue. And we know because we add a positive here, make that add a positive, we get 5. And then we're adding 2 and we get 6. So you can also, if you're trying to explain to somebody why subtracting a negative is the same thing as adding a positive, you can also show them with a pattern. You know, everybody learns different ways and they need it seen a couple different ways sometimes. And so that's just one more way we can look at it. You know, math is all about patterns, so that's a great way to show with that pattern there. All right, finally today we're going to talk about integer multiplication and division. And the first thing we're going to look at is the chip charge model, which for this case we got 3 groups of +2. So it's almost, you could call it chip charge, but we could also look at it as kind of like the array model we did with whole numbers back when we multiplied those. So if you have 3 groups of 2, I'm just going to pair those up like this and then clone them a couple times over. And I'm fine if you leave it like that, like an array model pretty much. So 3 groups of 2, there you go. This is 5 groups of -4. So I'm going to pull out -4 reds. And so you don't have to watch me drag out 20 of these. I'm just going to clone those as well. And it'd be helpful, I guess, if I move this out of the way. And so there are 5 groups of 4 right there. Now, 12 divided by 4. Let's look at that. I'm going to put out 12 positives. So let me do that. So there's 12 positives, and I want to divide those into fourths. So here's a case where if I'm just trying to divide these out, let's suppose we divide it incorrectly. You're a student, you got 12 there, and you're trying to separate them. So you say, okay, there's 4, there's 4, there's 4. Actually, that's not incorrect. We've divided it by 4, and my answer is what? 3. So I put them into groups of 4, and I got 3 as my answer. You could also look at this. Maybe you're a student and you're grouping them like this. And so now I'm putting them into groups of 3, and how many groups of, well, it took me, groups of 3 by putting them into 4 different groups. 4 different groups of 3. So here my answer is 3 this way. It all goes back to that partitive quotative division that we talked about last week. But either way, so long as you understand what's going on, your answer comes out to be 3 as well. I'll take either one as a correct answer. -9, same thing. We're just dealing with negative numbers here. So let's put out 9 red chips. And so there's 9 negative ones there. We're dividing it by a +3. So you could put them into groups of 3. And you get 3 groups of 3. So either way you go there, your answer is -3. with the chip charge model, there's not a nice, easy way to divide by a negative or show that. It's just kind of hard to show dividing by a negative with, because we're talking about positive number of groups. How do you have a negative number of groups? So you really can't show like -9 divided by a -3 and why that becomes a positive or anything with the chip charge model. We can also show multiplying, dividing integers on the number line. So let's take that example of, let's do -9 divided by 3 right here. So we got -9 right there. And now we can just divide it up into groups of 3 by doing this. 1, 2, 3. There's one group. 1, 2, 3. There's our second. Let's use different colors here. And then 1, 2, 3 there. So I've got 3 different groups there that made that -9. So my answer is going to be -3 there because they're all in the negative realm. So you can use the number line. I like the chip charge model, but you can also use the number line doing it that way as well. Multiplying, you can say what is 5 times 2? And you can say, let's clear this out. So just with multiplication, you do the same thing there. Let's actually make one of them negatives. Let's do 5 times a -2 because we did everything positive and we talked about whole numbers. So you could say, all right, I've got -2, add another -2, add another -2. Remember, multiplication is a simplification of addition, so it should make sense that I'm just adding -2 5 times when I'm showing it on the number line here. And so I get my answer to be -10. One final thing I want to talk about is just why does a negative times a negative equal a positive? So there are a couple of ways that we could look at it. One is kind of going back to the patterns we talked about before. So let's look at, say, 3 times 4, 3 times 3, and let me write this all the way out. So let's fill this out. 3 times 4 is 12. We get 9. We get 6, 3, 0. We can see that each time as we decrease this by 1, the number we're multiplying 3 by, we are actually subtracting 3 from our result. So it makes sense that when we get to 3 times -1, this should be a -3, and 3 times a -2 should be a -6. But what if the 3 was negative? Well, if the 3 is negative, what happens to our pattern on the right then? Then on the right, we're going to get -12, -9, -6, -3, and 0. And notice this time around, we're adding 3 in between each step. So we should be adding 3 right here, adding 3 again, and now we're getting positive numbers when we multiply a negative times a negative. So that's one way you could explain why a negative times a negative is a positive. We could also look at it in terms of debt. If you want like a word problem for it, let's suppose I've got a Netflix subscription and it is $12 a month. I don't know how much it is. My wife takes care of all the bills, but I'm going to assume that it's $12 a month. That's not really a positive 12 I'm getting each month. No, I'm paying a negative amount. Out of my bank account flows out negative $12 every month. So for a whole year, times that by a positive 12, that gives me negative $144 I spend just to search Netflix and can't find anything to watch, right? Well, what if, as a Christmas gift, my brother says, you know what, I'm going to pay for your Netflix for a whole year. Very generous of him. He's never done that, but let's say he wanted to be generous to me and do that. Well, that is taking away debt from me. I no longer have to pay that debt. So if I don't have to pay that debt, it's like he's taking away or subtracting these 12 months from me. So in essence, his gift to me is like him writing a check for $144 to me and saying, do what you want with it, and I buy Netflix with it. So I've gained $144 because someone removed that debt from me. So if you're looking, if a student wants more of a concrete example of why, like where in the real world we'd have a negative times a negative equaling a positive, you could come up with maybe some debt examples and show them that a negative times a negative is a positive. Now, to the next question, why is a negative divided by a negative always a positive? You could do some pattern searching. You could do some concrete examples with debt like I showed you here. You could also use that, the opposite of multiplication is division and show how those relate. I like to use an example dealing with fractions. If we have A divided by B is equal to C, this would work, assuming B is not 0, because B times C equals A. And if your students are at a point to where they can understand that, I think this will be a good way to show a couple of things. So for instance, let's say we had 6 divided by 2. What does that equal? That equals 3. Why does it equal 3? Because 2 times 3 is equal to 6. If I have 100 divided by 5, that equals 20. Why? Because 5 times 20 is equal to 100. Let's throw in a negative number. What if I had negative 12 divided by 4? Well, that's a negative divided by a positive. That equals negative 3. Why? Because 4 times negative 3 is a negative 12. What if I had the negative in the bottom? So if I had, let's see, 9 divided by negative 3, that also equals a negative number. Why? Because negative 3 times negative 3 is a positive 9. But what if I had two negative numbers? What if I had negative 36 divided by negative 9? That equals a positive 4. Why? Because negative 9 times positive 4 equals a negative 36. If I had negative 25 divided by negative 5, that equals positive 5. Why? Because negative times a positive gives me that negative right there. Okay, so there's a couple of different ways if those questions come up, but like I said, I want you to just learn things because that's what you're told, like that's the rule, and you do it. I'd much rather my students have a better understanding of the math, better number sense, and hopefully that if they ever teach it to someone else, they can, teach them the same tricks there as well. All right. Thank you for watching, and let me know if you have any questions, and have a good day.